We are in Rosen, Discrete Mathematics and its Applications, section 5.1, where we introduce the proof technique called mathematical induction. Here is a summary of the topics covered in the chapter. All right, so let's start with an example, a motivating example. Let's suppose we have an infinite ladder, and I tell you that if we can reach any particular rung on the ladder, then we can reach the next rung. And here's an illustration of it. And the question is, can I reach every rung on the ladder if this statement number 2 is true? And it turns out that's not enough information. We need to have one more bit of information, and that is the first statement, that is, we can reach the first rung on the ladder. So if I take these two together, then I can reach the first rung on the ladder, and then then I can use rule 2 as many times as I need to reach any particular rung on the ladder. And that's what this paragraph states. So with these two bits of knowledge, I know that I can reach every rung on the ladder. And this is, again, tries to motivate proof by induction. Here's how it will work. The way that mathematical induction works is we prove propositions. So we have here Pn, that is a propositional function. We want to prove that it's true for all positive integers n. And then we'll do these steps. The first one is the basis step, to show that the proposition is true when n equals 1. And then we have an inductive step where we assume the proposition is true for some arbitrary k, and then we show that it must be true under that assumption for n equal k plus 1, and that this implication holds for all positive integers k. Usually when k is assumed to be arbitrary, we capture that. All right, so then to complete the inductive step, we have to assume the inductive hypothesis. We'll abbreviate that the IH, and that is PK. And then we show that PK plus 1 must be true. So for our previous example, the basis step is by noting that we had a statement, number 1, that we could reach rung number 1. And then for the inductive step, we had said if we reach PK, we can reach the next rung on the ladder, so that PK plus 1 is always true if PK is true. That means PK implies PK plus 1 for every positive integer k. That means we can reach every rung on the ladder. Let's look at it more symbolically. Here's a way we can describe mathematical induction using propositional symbols. Here we have P1, that's the basis step. So if P1 is true, and here we have the inductive step after the and. Here's the inductive hypothesis, PK. And if PK implies PK plus 1 for all k, then for every n, P of n will be true. So there's the basis step, there's the inductive step, and when we complete those, by implication, the statement will have been proven true for all positive integers n. All right, again, there's the domain. We can shift this around. We'll talk about that later. Importantly, we don't assume that PK is true for all positive integers n. That would be assuming the consequence. We assume PK implies, then we show that it implies PK plus 1, and that implication is true for all positive integers. Yeah, for arbitrary k, if PK is true, then PK plus 1 is true. We can shift the starting point around. We often start at n equal 1, but we can start at any place as long as we're going up from that point. And how do we know that mathematical induction is true? What can I relate it to besides the latter example? Well, it's actually related to a very important property called the well-ordering property, which is one of the axioms of mathematics. And it states that every non-empty subset of positive integers has a least element. And I recommend you take a look at Appendix 1 if you're not familiar with the mathematical axioms. All right, let's show how mathematical induction follows from the well-ordering property of the positive integers. What we're going to do is we're going to assume both of the hypotheses for the mathematical induction logic. The basis case and the inductive case is true for all. The inductive step is true. And then we're going to assume that there is an element, at least one element, such that P of n is false in the positive integers. So we're setting up a contradiction. I'm assuming the left half of the implication of the conditional is true. I'm assuming the right half is false. And if it's false, there's a set of positive integers for which Pn is false. In other words, that set is non-empty. And we can apply the well-ordering property to that set. It has a least element. We're going to call it M. Well, we know that M cannot be 1 because P1 holds from our assumption. And since M cannot be 1, then M minus 1 must be a positive integer. And since M minus 1 is less than M, it cannot be an S. That means P at M minus 1 must be true. Now, since the other part of our assumption is true, pk implies pk plus 1 for all positive integers k. That means pm must be true since pm minus 1 is true. And this contradicts pm being false. So the result of that contradiction is we must conclude that Pn is true for every positive integer n. All right, so that's how mathematical induction relates to the well-ordering property, the positive integers. Let's look at how we can use it to make a proof. We want to prove the well-known formula that the sum of the first n integers is n times n plus 1 over 2. And in general, mathematical induction doesn't give us insights into mathematical relationships. We have to come up with those by another means, and then we'll use induction to prove them. All right, well, let's prove it for all positive integers n. We'll have the basis case first. The basis step, P1 is true, since if we plug in 1 for n, we get 1 times 1 plus 1 over 2 is 1. All right, and so let me say that this is Pn. Now we're going to state the inductive hypothesis, Pk, that is, that the expression holds for arbitrary integer k. And now we want to carry out the inductive step to show that Pk implies Pk plus 1 for arbitrary k. Well, we must always use the inductive hypothesis somewhere in any inductive proof. So we're going to do that right away in this case. Then we're going to add k plus 1 to both sides. So the inductive hypothesis is contained here and here, the equality of these two expressions, 1 through k and k times k plus 1 over 2. And then I'm going to add k plus 1 to both sides, which I'm allowed to do by algebra. And now I will resolve the right-hand side by factoring out k plus 1 to get k times k plus 1 plus 2 times k plus 1 all over 2. And now so I combine those by giving them a common denominator. Now I will factor out k plus 1 to get k plus 1 times k plus 2 over 2. And now we can see that if we take the entire left side and the entire right side, I have established that pk plus 1 follows from pk, and we have proven the result by mathematical induction.